Hello everyone and welcome back to the channel. I'm really pleased to say this channel now has over 1,000 subscribers, so thank you all very much for continuing to be interested in my content. Today we're going to look at things you didn't know, which is to say physiological complexity. Now, I got into this field a number of years ago, but the thing that always strikes me about it is that whenever I present anything or any of my colleagues present anything, people often come up and say, oh, that was really interesting, but I didn't understand a word of it, or I just couldn't get my head around it, or I don't really know what it's all about. So what I want this video to be is essentially a really, as far as I can make it, a basic primer on this particular field of research. And it's an absolutely fascinating one, which starts quite mathematical, but also has some really important biological implications. And so we're going to start with this. This is the Mandelbrot set, and this is essentially a mathematical representation, if you like, of fractal behavior. So I apologize to any mathematicians watching this thinking, no, it isn't. That doesn't look like that at all. But what this really shows is, if you like, one of the basic points about complexity, and that is that with very simple rules, you can produce extremely complex patterns of output, in this case visual representations of mathematical formulae. And these are fractal patterns, which means that if you magnify them you get self-similar patterns, so things keep repeating themselves time and time again, and this will go on essentially forever. And we also see some of this play out in biology, and it's not just in human biology, but in essentially all forms of nature. You can find these fractal patterns, and I've mentioned this before. The reason these things are interesting is because fractal structures can be produced from very simple rules, and so you can get a very large, very complex structure like the lung and the respiratory tree, with essentially two rules. The one rule being make a tube, the other rule being branch the tube. And if you carry those rules on at different scales, you get different size tubes and go all the way down to the point where you're able to exchange gases in the alveoli. And that's essentially what the lung is. And if you think about the structure of the lung, we call it the bronchial tree or the respiratory tree because trees are essentially the same kind of structure. And I think that's rather interesting that trees pump out oxygen, lungs are there to absorb it. So you get the same structures doing the same things but in reverse. So I find that really quite intriguing. But we also find fractal structures, self-repeating, self-similar structures in other things that we can measure. So here we have an example of spatial self-similarity, which is what you saw in the case of the lung. So as things branch off and carry on branching off, they have the same basic shape, but they occur at smaller and smaller scales. We can also have temporal self-similarity. So here's a plot of heart rate measured over 300 minutes, and then you zoom in onto 30 minutes, so 10 times less, and then you zoom in on 3 minutes, 10 times less again, and you see essentially the same pattern playing out. There is a similarity across orders of magnitude. And when we analyze these sorts of things, we start to then think about what that represents in terms of noise color. And I'm not going to spend too long on noise color, just to say this, that white noise, as you see here, is when you have the same power across all frequencies. So that's why it's called white noise. It's the same as having white light. You have all colors of light in the signal. But here we have 1 over f noise. This is called pink noise, and this represents a fractal pattern. So this represents this temporal self-similarity. We also, though, have Brownian noise, or sometimes called red noise, and this is where you have not 1 over f, but 1 over f squared. And essentially what that means is that you have a slightly less complex pattern. This is what's called a random walk. And so essentially this is the most complex kind of signal, this self-similar or self-affining signal. And then deviations away from that is considered less complex. So white noise is less complex than pink noise, and Brownian noise is also less complex than pink noise. But it's a very important point to make right now, is that there aren't any, or there's no single metric that gives you an answer what is complex, what is not. We essentially assume complexity from the signals we measure and the algorithms we use to measure them. And I'll come on to those a little bit later on. Then we can think about chaos theory. And what chaos theory essentially says is that simple systems can produce very complex output. So here we have the classical example of a double pendulum. And you can see, although the rules associated with the motion of this pendulum are very simple, you've got essentially two pendulums stuck together, and they essentially obey laws of angular momentum conservation, and also you can basically build a physical model, so you have some kind of gravitational pull on it. But the output is extremely complex, as you can see here. Now it starts to produce patterns you might see. We'll just run this through again. It starts off being as you might expect it, but then it starts to become increasingly difficult to predict what's going to happen next. And the thing about chaos theory is that simple systems can produce complex output if they are very sensitive to the initial state of the system. What do I mean by that? Here's an example, a slightly easier example to get your head around. So this is a double pendulum, and this is three different double pendulums with very slightly different initial conditions attached to them. In every other respect, these are absolutely identical. And we'll just let this run out. Here we go again. Very slightly different initial conditions, producing wildly different behavior across those three double pendulum models. So everything else about them is exactly the same except their initial conditions. And you can see you get chaotic behavior because you cannot predict the behavior of one from the behavior of another. This is called deterministic chaos, because in principle the motion of these pendulums is entirely able to be determined from basic mathematical structures or mathematical equations, but their initial conditions, the sensitivity to those initial conditions, produces very complex chaotic behavior. But hang on a minute, well, why is any of this of any interest to biology? We've already seen the heart rate traces I presented earlier, but there was a really influential paper written by Peter Macklem back in 2008, and it's well worth reading. And essentially it was looking at emergent phenomena and the secrets of life. And Macklem's central thesis was that life can only occur in a phase transition between order and chaos. You can't have too much chaos, because then you end up with very large fluctuations that are impossible to control, such as the weather. So that's unstable, and you really can't control anything there. You just have to let the thing play out. But you don't want anything to be too stable either, because that becomes inadaptable. So crystals are the classical example of something that's entirely stable, at least once the crystal has formed. Life has to occur somewhere between those two extremes. It has to be ordered and stable, otherwise you wouldn't last long enough to reproduce. But you live in an environment that's ever changing, so you also have to be adaptable, and that requires fluctuations in your output. In other words, anything under homeostatic control, something with anything with a metabolic rate, is going to require these fluctuations in order to be able to survive. And that's where physiological complexity comes to the fore. So how do we look at complexity? What are the analyses we can do to quantify this kind of thing? Well, fluctuations in any time series can be analysed in a variety of different ways. So we can look at the magnitude of fluctuations. So for that we can use the standard deviation or the coefficient of variation. Now that takes no account of the data order, and it essentially quantifies the magnitude of variability, or the steadiness as it's sometimes called, in the signal. So that's simply standard deviation or coefficient of variation. Then there's the temporal pattern of those fluctuations, and that's what complexity is usually trying to quantify, or at least the statistics we use and call complexity is essentially trying to do. Now these things are imperfect, but there are a number that we can use. So we can use entropy measures. So we can use approximate entropy and sample entropy. And what these statistics quantify is the regularity of the signal. And a really simple example, that my wife and collaborator Sam Winter once came up with. Let's just have a look at these two examples of words. So here we have a word which is made up of the letter H versus a word made up of HELLO. The latter, the hello, is less regular. It contains more information and therefore it has higher entropy. And what we're trying to do with append and sampend is attach a number to that regularity. So when you perform an append or a sampend analysis, and there's a reason why you might do one or the other, but I won't go into that now, the range you get is from 0, which is completely predictable like a straight line or a very clear repeating pattern, to 2, which you get if you were trying to quantify white noise. Something in between those two extremes is where you usually find append and sampend. Then there's fractal scaling. This goes all the way back to the initial Mandelbrot set, etc. So trying to look at the self-similarity of the signal, the degree to which it is. And to do this, you have to detrend the signal, you separate the data into boxes of different sizes and different scales, and then you essentially do a regression analysis on each of those boxes. And then what you have is a plot of a series of best fits, and then you fit a line through that, and you produce an alpha exponent. And if that alpha exponent is 0.5, then that is white noise that you're looking at. If the alpha exponent is around 1, then you're looking at pink noise. And if the alpha exponent is around 1.5, then you're looking at Brownian or red noise. And what this can do, as I've already said, is detect self-similarity or self-affinity. And what we tend to do is use both of these measures as a means of quantifying complexity. Most of the time, if append goes down, in other words, the signal gets more regular, then the detrended fluctuation analysis alpha exponent will go up, away from 1 towards Brownian noise. So they tend to agree with one another. All of these measures have their pros and cons. So detrended fluctuation analysis has the problem of needing a very large amount of data, several thousand in fact, before you get a stable analysis using DFA. Append has some problems in terms of counting its silhouettes, well not its silhouettes, its I can't even remember the name of it now, it escapes me, the templates, that's the right name, the templates, it counts its own templates twice. Sampend doesn't do that, but if you've got lots of data, then that doesn't really matter for append, as I'll show you in a moment. Anyway, the key point is you can define complexity using these statistics, but there isn't any single statistic that actually quantifies complexity. How has this been used historically? Well, the first group of researchers to really look into this was Lipsitch and Goldberger in 1992. And they were arguing that one of the signals of aging and disease is a loss of complexity in time series and also in physiological or anatomical structures. And one of the ways they looked at this was to show 8 minutes of resting heart rate data in a young participant and an old participant. And so if you quantify these using magnitude statistics, this is what you get. So their heart rates have the same mean value, 65 beats per minute, and they also have the same standard deviation of plus or minus 4 beats a minute. So in terms of the magnitude of variability, there is no difference in these time series, but you look at them and you think, actually no, the old subject's time series is very different from the young individual's time series. And you'd be absolutely right, because when you apply append to these data, what you find is the young participant has a signal that is twice as complex, or we might say the old participant, we can be absolutely accurate in its use, the older subject has a time series that is twice as regular as the young participant. So clearly here, these complexity statistics can tease out characteristics of a time series that standard measures of variability cannot. And that was really interesting when I first picked up on this, because at the time when I first looked at this, I was working on fatigue. And what I found, and this was when we were doing work in Aberystwyth on a biodex, And here's the first minute of contractions. So you can see there's fluctuations in the torque, as you always see. And this is at task failure. And what was interesting is there's clearly a repeating regular pattern in here in this particular subject. You don't necessarily always see that, but there was clearly something going on in the fluctuations in torque as a consequence of fatigue. And I really wanted to study that. So alongside my wife and long-term collaborator, Sam Winter, we decided to look into this when we got to Kent. And so she's an expert coder, a very, very good mathematician. So she was able to extract all of these complexity statistics for us. And then we recruited Jamie Pethick, now Dr. Jamie Pethick, who did his PhD on this. He's now at the University of Essex, which amuses me greatly because when he writes ethics documents, Jamie Pethick is writing ethics for the University of Essex. Anyway, I digress. Jamie's first study, which was published in the Journal of Physiology, showed very clearly the pattern that occurs with fatigue. So here's the first minute. You see these are raw data now. So what we didn't do was filter them because we don't want to take any assumptions about where the complexity is in the frequency spectrum. And we simply apply these statistics to it. So this is the first contraction, or the first minute of contractions. This is an example contraction from that. AppN 1.1, SARMPN 0.98. If you've got enough data, these two will be very close to one another and will share the same pattern in terms of any changes. And then DFA alpha is close to pink noise in this case. And then in the last minute, around the point of task failure, the AppN has dropped to 0.3, SARMPN has dropped to 0.29, so you see a correspondence between those two, and DFA has moved towards Brownian noise. So we demonstrated in that paper that fatigue definitely reduces torque complexity, but we had no idea why. And a spoiler alert, we still don't entirely know why, and we're working on some really interesting data at the moment, which hopefully I'll publish later this year. And when I do, I'll obviously do a video on that. But we did start to explore this using Jamie's PhD as the vehicle. So the first thing we actually wanted to know was, is there an intensity relationship between complexity and its loss with fatigue? And indeed there is, because it appears that this fatigue-induced loss of complexity only occurs if you do contractions above the critical torque. So critical torque isn't just a metabolic threshold, it's also a threshold for a change in neuromuscular behavior in terms of the fluctuations in the torque signal. So these are contractions performed for 30 minutes below the critical torque, and these are the contractions above the critical torque. You can see a systematic decline. And it doesn't really matter what the intensity of the contractions are above the critical torque, you end up with the same end-test entropy or end-test DFA alpha exponent. And so you seem to reach a limiting level of neuromuscular complexity at task failure, which is extremely interesting. But where was this coming from? So we wanted to do a series of experiments to find out why. The first thing we looked at was peripheral fatigue, and the way we did this was by doing contractions to task failure, then waiting 3 minutes, then doing another series of contractions to task failure with or without occlusion. So here we have the first bout, and you see AppN 0.64, DFA 1.01 in this particular case, and then we did these contractions to task failure, waited 3 minutes, and then started the contractions all over again. This is the first minute of those contractions all over again. And you can see AppN is approximately the same, DFA is slightly higher, so there was some residual fatigue there, but not a lot. It didn't consistently change the complexity analysis. But what we did when we occluded the muscle, so we performed this same first bout of exercise to failure, then we waited 3 minutes, but crucially, we had a cuff on during those 3 minutes, releasing it only when we started the contractions again, purely for participant comfort. But in the first minute of these contractions, there was no recovery whatsoever of complexity. So complexity, you can see, was still very, very low, and this is reflected in those two complexity metrics. So a very low AppN and a DFA alpha above 1.5. So this shows peripheral fatigue appears to be a major player in the loss of torque complexity. And you'd expect that, given that this only seems to occur above the critical torque, which is where peripheral fatigue really starts to kick in. But we thought maybe there's something else going on here. Maybe that's not the whole story. And one of the other things we looked at was caffeine administration, because we know that caffeine has significant central effects. It's an adenosine antagonist. And so what we're trying to do here is manipulate the central fatigue effect by administering caffeine. And what you see with the placebo condition, we had task failure occurring in just over 7 minutes on average. And then we have the caffeine condition, which extended time to task failure up to almost 10 minutes. But crucially, at the ISO time point, so at the point of task failure in the placebo condition, the complexity loss was a lot less in the caffeine condition. This was associated with no differences whatsoever in peripheral fatigue throughout these bouts of exercise. So peripheral fatigue developed to the same extent in both cases. What was different was the voluntary activation, our measure of central fatigue. So voluntary activation was better maintained with caffeine compared to placebo. In other words, although peripheral fatigue appears to be the major player in the reduction in complexity with fatigue, central fatigue is also a contributor. And so what the loss of torque complexity means is that both central and peripheral fatigue are at play. Peripheral fatigue being the major factor, central fatigue also being a contributor. And this has led us to suspect that what's actually causing that loss of complexity might be centered at the behavior of the motor unit, and that's the work we're working on right now. So, to conclude, complexity appears to be a key feature of integrative physiology. Homeostatic control necessitates fluctuations, and you can't have control without them. The variability measures that we've made historically quantify the magnitude of fluctuation, so standard deviation and coefficient of variation. They are great to use for understanding some of the structure of the signal, but they don't show you the whole story. Complexity, on the other hand, analyzes the pattern of fluctuations in one way or another, looking at fractal structures or looking at the regularity of the signal. It's been shown that both aging and disease reduce physiological complexity, but it's also now been shown that neuromuscular fatigue reduces complexity exclusively above the critical torque, and that is a consequence of both peripheral and some central fatigue. And why is the loss of complexity important? Well, if you lose complexity, it's thought you lose adaptability. And in the case of the neuromuscular system, if you have less complexity, you're more likely to produce movement errors. Those movement errors could involve falling over, dropping objects, or not being able to complete a skilled task, or in the case of simple isometric contractions, reaching task failure and not being able to produce the same torque time and time again. So hopefully that's given you a little bit of an insight into what complexity is and what I've spent the last few years using it for. Thank you very much for listening. I hope you enjoyed that. Give it a like if you did, subscribe if you did, if you haven't already, and thank you very, very much for listening.